Okay, this little PowerPoint is going to focus on speeds and feeds. We're going to define all this, and I'll show you how to a nifty way to do this in the end. Let's go back over the variables. We've been talking about it with the mill and the lathe. Um, the lathe, the speed, you'll talk about the related, it's how fast the material's turning the material. The fast the motor's turning the material. With a mill, it's how fast the cutter is turning. And the feed is how fast you're running the cutter down the part, the sending speed, or as it was called, the feed rate. In the mill, same thing, it's how fast the part is moving past the cutter. Depth of cut is another variable. Come to that in a minute. Are there other variables? Yeah, materials. We'll get to that in a second. But let's define that speed. Um, and it's actually measured in surface feet per minute. And even though I'll show you how you do it here in a second, but it is a combination of the speed of the rotating speed and the feed, the sending speed. On a lathe, it's kind of easy to see. You got a single point, and how much material is going past that point, how many inches per minute it's going past there, is pretty easy to calculate. It's a little bit harder, but it's still the real key part is in terms of that feed is how fast the material is running past the cutter. Okay, so define speed as how fast, in inches per minute, how fast the material is going past the cutter, or it could be feet per minute, some linear measurement per minute. Now, one of the other key parts is machinability. In the mid to late 1800s, they really were trying to establish how to make consistent steel, particularly for the railroads, because you wanted to have railroad tracks that were consistent. And so they decided to use a particular mixture of carbon steel, 1112. It's a mild carbon steel, nothing in there much but carbon, a little manganese, and then iron. And it has 0.12% carbon. It's really very soft for steel. It's easy to machine, and they said this is going to be our reference. And so they assigned that a value of 100. Anything less than 100 was going to mean that it was harder to machine. Any number larger than 100 meant it would be easier to machine, and you would grade stuff accordingly. And you might think this is arbitrary, but they do actually have some calculations with this. If you get into this, pretty tough. So if a material has a machinability of 50, it's hard to machine. Now keep in mind that this scheme was put together by the American Iron and Steel Institute before aluminum was readily available to be as a machined product. They did have brasses and bronzes, but it's mainly designed to go around steel. And here's an example of a chart. The more carbon you put into steel, to plain carbon steel, the better. Over in the less carbon steels, you'll notice those have numbers larger than the last two digits of the 1112 steel. Those last two digits indicate how much carbon is in there, and less than 1 by percent point. If you look at there's 1095 that has a machinability value of 42. That means it has 10 indicates just a plain carbon steel, and it has 0.95% carbon in it, and it's pretty hard to carbon. In fact, I believe that is the same carbon content that A2 tool steel has in it. And it's also the same machinability rating. So higher the carbon content, up to 1%, the harder the steel is to cut. And that last two digits works the same on those alloy steels. I think you're looking at a lot of chrome molybdenum steel over there. So it's got chrome, moly, iron, and say 0.42% carbon. Okay, there's the chart. Notice in the middle at the bottom, aluminum, very high numbers, 360%, much easier to machine than 1112 steel. One other variable is the type of cutter, and that is going to make a difference. The harder the cutter, the higher speed and higher feeds you can go. So we've looked at all the things. We've defined speed. We've looked at the variables. So how do you actually do it? One way is to look it up on a chart. And here's something, whatever the chart, figure the diameter of your end mill, and if you're doing aluminum or plastics, you would go at those particular speeds, and those are the recommended feed rate, the surface feet per minute, or the inches per minute of your what's running past your material. Then you have your low alloy steels. That's basically carbon steel and the 1000 or 1100 series steels. And there's a calculation. There's a recommended range. And not all machines can dial in an exact number. So you can use a speed chart. You can do a calculation, and I think I've taken the link, the machinability link off. You can find it, but you looking at the RPM. That's how fast your cutter is going to be, or your lathe is going to be turning. The sending speed, the feed rate, with because all of these are related to something round. The cutter's round, the material's round in the lathe. You're using pi times the diameter, and you end up with, you can do math and you can move it around if you want to figure out the speed rate, but you know what your RPM is going to be. You can just simple substitutions can work. So you can sit here and calculate it, and Machinist's Handbook have lots of formulas. That includes the material factors. But guess what happens in this modern world? There's an app for that. Enter speed and feed calculator into your Play Store or iTunes or whatever, where you get your podcast or your apps. You'll be hit with a bunch of them. Some are better than others, but and some are free. All the ones I got on this screen capture I think are free. You can pay for some. I use one that is free. And let me show you how they work. First thing you're going to get is a disclaimer. This coming right after presidential campaign rally, where disclaimers for something that they're claiming didn't exist. Anyway, it'll say, hey, we're just running the math for you here. You enter something wrong, you got a bad machine, it breaks, don't come blame us. Fair enough. So here's the page at which you would enter stuff. You tell it the tool diameter, you select what kind of end mill it's going to be. Any of the other stuff, it's either a pull down chart or you type in a value, and you want to be using about particular depth of cut, would be a finishing cut on aluminum, but you might want to put something more. You notice at the bottom, we picked carbon alloy steel. This is material that's going to have a range of carbon in it between 0.17% and 0.29% carbon. I hope you heard that point. It is not 17%, it is 0.17% carbon. You push the button that says calculate, and here's what you get. You'll notice the top, 1/4 inch diameter end mill, 2 flute, no coatings, in high-speed steel. The material is going to be one of these types of within this range of carbon steel. And they say set your RPM at 1956, and for your feed rate for roughing cuts, you want to go 2 inches per minute. Kind of slow, but pretty hard stuff. For your finishing rate, you want to go half that. Oh, here's aluminum, 6061. All the other stuff is the same, but here you have an RPM of much higher, and your roughing cut would be what the feed rate would be, how fast you would turn the handles, how fast you can move the cutting head along for that. It gives you some other stuff that's off the screen, but I just wanted to show you this part first. Here's copper alloy. Just a general copper alloy with the same parameters. And here is naval brass, which is also a copper alloy, but it's just a slightly different version of a copper alloy. And so you'll see that's fairly similar RPMs and feed rates. And here's what it is if you entered nylon as the material you're dealing with. Pretty high RPM, not as high as the aluminum, but one of the things when you're machining plastics, you don't want to go too fast because you don't want to start melting it. Since it takes a little bit different approach to it. So, you get into a place where you really need to calculate speeds and feeds, pull up a free app, let them do the calculations for you. But in this class, you're going to be machining. You could be running machine slow for steel. We're actually not going to machine any steel. It's going faster with aluminum, and actually the kind of plastics we do, we're going to go even faster. Depth of cut, which is always that question. 100 thousandths, 0.1, 1/10 of an inch is pretty good for a roughing cut, half that for a finishing cut. And so use those as general estimations for when you're running machineries like we have.